So today I have the privilege to welcome our distinguished speaker, Professor Michał Kracik, an associate professor at the Faculty of Industrial Design, Department of Design Methodology, leading the Design for Extreme Environments Laboratory, who is a former head of design and co-founder of the design company MXene. MXene, yes, is this correct name? Yes. Yeah. His primary research interests include human space exploration, human spacesuit interaction, and spacesuit design. He conducted his research at the MIT Department of Aeronautics and Astronautics as a Fulbright scholar, and later as a Kościuszko Fellow postdoctoral researcher. And he was working at NASA-funded projects. He is design consultant, advocate, and educator. So it's a privilege to have you here, and the floor is yours.
Thank you very much. Thank you very much. Welcome. It is really my pleasure to be here, and thank you for the invitation. This is the part that I like the least, the introduction, but I thought that it may be necessary just to say a few words, not about me, but about my experiences, because even though I am an industrial designer by training, I have been working with engineers for 18 years now on very different projects, and not only space related, but also product design and transportation design. And so I have a huge respect for engineers, and I have been always, even like the founding of the MXene agency was based on this notion that design and engineering are so interconnected that it is very always beneficial to work in close collaboration. Today I would like to talk about a few different projects and few of my experiences and share those with you. And but to begin with, I thought that it will be interesting to start with a historical context. So it kind of proves that industrial design has been involved in human space exploration from the very beginning in two different contexts. So one example I will just briefly talk about was lunar lander, and the second one was Skylab, the first US space station. So lunar lander, everyone knows how it looks and what was its function and how it was operated right now. But at the beginning, there was a very there was several problems with it, and most of the biggest problem was the weight, and the company that developed the lunar lander was struggling with that issue, and the source of it was mostly because of the windows, and the approach was a traditional helicopter style approach where the cabin landing cabin should be kind of spherical and has a very good visibility, and you need seats for the operators of the lander, and so that was a standard in the industry. And just at the moment where they started building prototypes, and a group of engineers, not designers, engineers, started to examine options to reduce the weight and to change the situation, they proposed to the engineering manager of this project, they proposed maybe we can get rid of windows, maybe we can get rid of seats, maybe we can put people in a standing position And it was a very difficult challenge to convince the leadership to go with that route. But it turned out to be a perfect solution. And the way how they convinced the leadership was by building prototypes. And the ones that you can think, maybe I will move. I didn't realize that we had this here. So the prototypes that they built were just simple prototypes out of plywood. And just by inviting the leadership team to see and experience how it could work when with all these changes, they realized that that's the only solution. So the shift was huge, but also the environment was so much different that it made sense for the astronauts to stand when landing. So the second example is more industrial design related, and it is related to the whole field in a very particular way, because the person who was involved in the designing of the Skylab was Raymond Levy, and he is one of the most recognized and famous designers of all time. He was active for 7 decades. He was designing everything from logo of for different renowned brands. He was designing cars, but at the end of his career, he was involved as a consultant in the design of the Skylab space station, and his involvement was very particular because he wanted to understand how people would operate, and he and his team produced thousands of sketches and ideas, and some of them came to life in the form of the space station design. And he introduced several ideas that were later on introduced into the design of the Skylab. He insisted on the notion of the connection with Earth. He introduced the circular window that you can see at in the middle of this top picture. He designed the table. He designed the shower. He designed many different elements of the station that were both technically feasible, but also from a humanistic point of view, they were important for the crew. They were taking into consideration a lot of psychological aspects of that journey. And what was interesting was that he was working very close. Not all of his ideas went into production, but he was very humble about this, and he later recognized this experience as a designer that was already extremely famous, that it was his most important experience in his career. I don't have to comment on this, but you can see clearly that with the development of ISS, I don't want to criticize ISS, but that the designer's involvement was non-existent there, and even the visual chaos is you don't need to analyze these two pictures to see the difference in approach. Obviously, this is not something that the function, the size was different, and I understand that, and the limitations, budget limitations were different, but it is something to consider when we look into the future, and currently developed space station like VAST are changing that approach and introducing a little bit more of functionality and humanistic elements to the design. So that was just this short introduction into the context of how industrial design can influence or contribute to the space, human space exploration efforts. So now I would like to speak a little bit about the studio designed for extreme environments. It's a studio at the Faculty of Industrial Design where I work and have been working for the past, have been working at this studio or leading the studio for the past 11 years. And this is just an example of an approach to teaching design through the lens of extreme environments. So the idea is to have a practical and also very strict constraints for students to work with. So they have to think in a different way. They have to understand things that we are not familiar with and things that we have not been adapted to through evolution. So the simplest example is gravity, but sometimes the way we understand it is not exactly precise, because even though it gives us this very interesting perspective and experience, we don't really understand all the different issues that may arise with changing that simple parameter of gravity. Not talking only about microgravity, but also lower gravity on the moon and other places. So the studio is focused on two areas. It's not only about space exploration. We also tackle some Earth-related problems. We try to find connection, but I will just focus and present this part that is related to space exploration. And I divided this to 5 different areas. These areas are, you can look for different ways to divide those, but this makes a little bit more order into this whole collection of projects. So I will not talk specifically about in details about specific projects, but I will just mention a few of the projects related to certain areas. So when we talk about Mars, we have been working with different constraints and with different in different collaborations on mostly on spacesuits and the travel to Mars, and that was a collaboration with NASA. And then we've also worked with the University of Boulder in Colorado on the hybrid spacesuits that could benefit the exploration efforts there. But also some of the work was focused on the humanistic aspects of being away from Earth and starting a new civilization and a new society. So we've also considered things like spending a free time and exploring and playing sports and taking care of plants or living organisms. So that was these are just few examples of the students' work. And then the moon is a little bit more close to us, and so there are more defined plans to explore the moon in the near future. And here the work was mostly related to solutions for the Artemis mission, and that these two projects that you can see are related to scientific exploration, and NASA was looking for solutions to have a simplified version, human-powered version of a vehicle or cart that can transport equipment, scientific equipment, from a base to a close locations to collect samples and to other activities. And that was a one semester project. Students came up with many different ideas. We've tried also test those ideas in VR, making simulations to see how this the different approaches can benefit users, astronauts in this case. Another area that students have been working on was related to zero gravity and how we operate in that environment. And because it's so different than the way we are familiar with, it's always a very interesting. It gives a very interesting perspective, and the way students work, they always try to understand how it is, and because we do not have a good way to simulate that, we are looking for different ways to either experience weightlessness or to imagine how it would work and what kind of constraints we would have to take into consideration. But the things that maybe that are interesting here and that I can mention now, and maybe I will just mention about it later a little bit more, is that it requires a new approach to ergonomics. So when we sit at the desk, it is not going to be the same. When we prepare food, it is not going to be the same. And we need to find or define the rules that would help future designers to provide solutions that are not conceptual, but that are possible and that are solving real problems. So another area that is very far-fetched, so to change a little bit perspective, is interstellar future. This is more like this is more related to speculative design that is that gives us a little bit more freedom in thinking about the future. The example I'm showing here is again a one semester project, 8 students team. That was a competition, international competition that challenged students with the idea of 250 years travel to another solar system. And what was interesting was that the competition rules required not only the general idea how the space would look and how the society would evolve. The constraint, among others, was to have between 500 and 1,500 people living on this spaceship. And but also the constraint was that all the solutions that we propose would have to be a TRL2 at least. So it was something that had to be feasible. And you can understand, I mean, you can obviously understand how difficult it was for industrial design students that have no experience in engineering to calculate, to come up with reasonable solutions. And fortunately, we had one of your alumni who helped us a lot. She was at the time our student. She defended her master's degree at AGH and then joined our faculty, and she was very helpful in making this this project, and the students got the second place in this competition that I think was a great success, because other ideas were much more on one hand they were more technical, but also less feasible. So I was very proud of them. I'm not sure about our timing.
Just more than 35 minutes. It's 1 hour.
Oh, okay. I don't think I'm going to go for that long. Hopefully, I will answer some questions. So this is another example that maybe Agata is a master of. We are just trying to consider that as a very important part of learning how to design for space and understanding what can happen. We do not have extensive project examples here, but that was one of the solutions developed for analog spacesuit design. It was a little bit too complicated, maybe, and not well funded to finish that and to make it more, I would say, even low scale producible. So, but it was a great experience for students to be able to try to physically build something and to physically imagine how the limitations would affect people in working in spacesuits. So, going back to the industrial design that is a part of an Academy of Fine Arts, which suggests that we are mostly doing nice renderings and sketches. I really try to push students to their limits, to understand the technical limitations, to understand how these systems could work, and to cooperate with engineers to verify their ideas. And one of the ways to verify their ideas was to present their work at conferences, but at technical conferences, which was an extra challenge for them, especially that they didn't even know what the conference poster was. They thought it was just going to be an image that will present their work. So that was one of the challenges. But again, they succeeded, and some of the projects were even awarded with some recognition. But on top of all the work that we have been doing, we try to share the vision of human space exploration with others and present the ideas and the projects to the broader population, to children, to young people that are looking for their career paths. And so we try to organize exhibitions and showcase the ideas in Poland and internationally. These are just a few examples of the work that students have been doing and visiting different places and sharing their experiences with children and other young people. and also take on some bigger challenges like building the space, the one-to-one mock-up of an interior of the Mars transit vehicle, which was a very interesting challenge for us, but it is no longer standing there. So this is the final slide, and here I want to thank AGH for the opportunity that we have been given to participate in MXene in Leo experiment, and I want to thank Agata for bringing me in here. I want to thank Shreyas for being a great collaborator, and I want to thank Professor U for trusting in us, and I just hope that it will follow with other projects. So that was the part of the student work I have been doing with students for the past 11 years. And now I just wanted to share two research projects that I have been involved in and say a few words about those projects. So the first one is related to the idea of a mechanical counter-pressure spacesuit. This is the idea that instead of air that is compressed in the balloon of a spacesuit, of a current spacesuit, you can provide the same pressure with mechanical force, and because of that, gain a lot more mobility, and also reduce some risks related to gas pressurized spacesuits. So the idea was first introduced in the late 60s. But then with no advanced materials, it was decided that it is too complicated. And then in 2000s, my professor from MIT, Professor Newman, started this project again, developing the concept of a mechanical counter-pressure suit. And my role within other areas, my main role was to design a helmet that was that would fit and that would also provide a gas environment for the head. And so one of the biggest challenges was to find a way to connect a very tight elastic material with a gas pressurized suit without getting too much limitation for the movement and for the visibility. So that was that started in 2010, and here are some examples of the approaches I have taken, and that resulted in a concept. I have to say with maybe not a disappointment, but it's still a concept. It has not been flown into space. It has not been tested. There are some elements of it that are functional and that are working in a proper way and providing enough pressure for the right functioning of the astronaut, but it has not been tested in space. At least I can say that the helmet, that SpaceX helmet, was inspired by this helmet. So that is the only thing I can say. So the second project was a little bit more related to a current situation. It was less conceptual in a way, and we had to examine how the interaction between a spacesuit and astronaut, what happens inside the spacesuit. Because the mechanics, the way the spacesuit moves is different than how physiologically we are designed. So there are issues related to that, and these issues results in injuries, mostly during training. Like major injuries occurs during training, and it's related to the fact that even though the spacesuit in the neutral buoyancy lab is being kept simulating zero gravity, but then the astronaut inside the spacesuit still is affected by gravity. So in the inverted position, what happens is that the whole weight is sitting on the shoulders or bearings that you can see here that are metal bearings, and it has caused several shoulder injuries in the past. So that whole study was also related to the way we move within the spacesuit. You can see here that astronauts, when they prepare for donning into the spacesuit, they have to add foam padding to their LCVGs, and this padding just allows them to feel more comfortable inside. And even though some astronauts prefer to be very tight in a spacesuit and other more loose, this is something that is necessary to adjust to the right comfort level. And you can see that these solutions are very analog and very old-fashioned. You just with the wire, you just attach a bag with the foam in a place that is most suitable for you. And so this work was later again. We've tested a lot of ideas, concepts how we can use advanced materials, how we can use materials that are that would be able to fit or to adjust during the training procedures, and that resulted in several elements, passive elements, but integrated better with the LCVG, and then active elements that use air pressure to regulate the spacing between astronaut and the suit. So that work was, from one hand, it was conceptual. From the other hand, we built a lot of prototypes. We worked with industry to manufacture these airbag ideas. Then they were tested with NASA. But the main outcome. So again, that was another. This is like a side project that was related to the astronaut protection garment. And then this is related a little bit to what you have done with MXenes. So we wanted to know exactly how the human interaction with the spacesuit is happening. So, and where are the pressure points? Where are the places that are the most dangerous? And also to understand how we move differently than the spacesuit. So that was one of the like side projects that was developed to measure the pressure in different points. And it was measured within the spacesuit. So the idea was to have more reliable data than just astronaut stories about how they feel comfortable, because you have to remember that most astronauts, they have this idea that they cannot complain, and so that caused a lot of these problems that they were saying always, "Oh, I'm fine, nothing happened to me, everything is okay." But then it turned out that there was a lot of discomfort, and that also led to certain risky situations. But the general long-term goal was to inform the design of a new generation suit that is better than the current one, that has less limitations than the current spacesuits. So I think with that I will end. If there are questions, I guess I maybe mistakenly thought I will have only 30 minutes, but I will be happy to answer questions and maybe go back to certain projects that I've mentioned and maybe say something more about them. Thank you very much.
And for very interesting talk, and I opened it to the
Another question. My question is, this is a conflict between the requirements of the functionality and aesthetic. Yeah? Because the functionality, reliability, and other things which we are waiting as an engineer from the product, sometimes it's in conflict with the aesthetics. Yeah, it can be noticed in any product, many products. Yeah, which is very bad to you, but very good. Yeah, to use. That's how you solve this problem as a fine art designer, because you take care for aesthetics, not for the functionality and reliability of the product.
Well, thank you for this question. I will say that I have to care about everything that you mentioned. That is why I'm here. I just want to convince you that we do care about the functionality, and the more constraints there are in the project, the more challenging it is to provide I'm not going to say that the aesthetics doesn't matter, but it has a function. For example, when you have an equipment that has to be extremely reliable, the role of aesthetics is that it has to communicate that reliability to the user. So, for example, you can have a very robust design equipment, but then maybe through the way it was the sharp edges, the way that the details have been treated, it kind of can communicate that it's not so robust. It can communicate that it has some flaws. And so even working with industry on transportation design products, even when we were doing, let's say, plastic elements for injection molding, we cared about the way the structural part underneath was designed. So it does. So it's not. So sometimes when you go into details, it turns out that what is aesthetic is also well engineered. So that's what I'm trying to convey here. I know maybe this is not very clear yet, and I would have to showcase, like, for example, in some cases you would have the strengthening structure underneath the surface of the housing for let's say I don't know, a mouse or a computer or something, and then you can, instead of having angles, 90-degree angles, you use hexagon, right? You kind of like you add little bevels, and that will also strengthen, and so I know maybe I went too far, a little bit too far into engineering part, but having been in touch with engineers for so much time. I was always looking to find a common ground and to find ways where where the aesthetic part can also be functional and can also communicate something more than just the beauty of the proportions or of the lines and things like that.
Okay, to continue this question, reach that. Thank you. Continue this question. If you have the order from the producer, for instance, for the car, for some aesthetic some parts design, you have got the functionality, you have got the mechanism, you can got the design, mechanical design or electronic design, and you design the aesthetics, or it's like in mechatronics that you are designing together with them.
That is the ideal solution, that we work from the very beginning together, understanding both sides and both constraints. So many times when, mostly in my professional work, that was the case. So the designer was present, or the designer had to know all the constraints from the beginning and try to come up with solutions that were acceptable by the engineer. But the ideal solution is when, at least from the beginning, there is someone who can provide some feedback for the functional and aesthetical side of the product. And I think it is possible both ways. Sometimes when we are involved at the very end, it's just more difficult, and compromises are more costly, and then usually designer loses with the budget and with time constraints. But I think, at least I have in mind many examples where it is possible to have a designer from the very beginning, and even if his role is limited, and even if his influence is limited, it will always be better than when he's not involved.
Okay, thank you.
Good experience in designing, studio designing team in automotive industry. And we have often the problem with manufacturability. Even for experienced engineers, it is quite tough to understand how the design will influence the manufacturability, the cost of the molds and so on. How did you take into account that with your project, with your designs?
So we teach students, like in the courses, they have materials and production procedures. So they have the basic understanding of it, and obviously they will never be as prepared as engineers, and I always repeat it and say, like, you have to be humble. The fact that you know that, like, this technology, how it works, doesn't mean that you know all the details. So be humble, but by understanding what are the basic limitations of the technology, what are the basic limitations of, let's say, regarding costs of tooling, that they know from the beginning that if they make the shape too complicated, it will require more tooling that will cost more. And so I think this is, again, they will not be experts, but they can understand the process and at least have a dialogue with engineers about it. And, yeah.
Required, especially the close collaboration with the manufacturers. So it's really good. Okay. Thank you very much. I understand that you have some let's say the computational tool which will help you to understand the whole process. So okay, thank you very much.
You said that your students in the Hyperion competition had to design something with TRL of at least 2, and I just wanted to clarify because that numbers means nothing. And what is TRL?
It's technological readiness level. So it means that the number 2 means that it's theoretically proven to be possible. So, for example, when we were talking about power management and propulsion, the ideas had to be somehow feasible, at least theoretically. So we wouldn't use dark energy or something to propel the ship. Yeah, so well, TRL9 is when it can go to market. So there, you can see the gap.
Thank you, Michał, for the nice presentation. I wanted to make a bit more of comments here. When I met Michał, it was a long time ago, I don't remember, 10 years ago, something like that. I thought that he's just a space artist, and I was designing habitat, and I needed suits. So of course we tested Michał's suit that was presented here, the gray one, maybe you remember, on the slides. And later I realized what a treasure he has. He's not only a space scientist, space artist, but he's also a space scientist. And in particular, now we are working professionally in one grant, which is Micropura startup. And we had several problems designing the sensor because we need to make it consumer friendly as a product. This sensor is measuring bacteria and fungi, something disgusting. And we were asking Michał how to sell this sensor in a way that people will like to buy it, that they will not feel disgust, that this sensor will be safe for humans, that it will not distribute bacteria, even more bacteria and fungi in the space. Then Professor, he just left, but he asked us, engineers, the group of engineers in the startup, this is too big. You need to decrease the size because nobody will like to have the big sensor on the shelf. So again, we asked Michał how to put so many sensors, so many parts of the sensor inside very small space. And again, for our engineer team, it was really complex. And then another thing, which is very critical for our product later on, is production. So again, Michał and his team have possibilities to design forms and design all technological line to produce the final product. We don't know this. We have no knowledge like this. And Michał's team can prepare all technical description of the device, ready for certification. So he has so many capabilities with his team to collaborate with us. But now I have questions for Michał. Thank you for already so hard work together with us. And exactly, this is a dialogue. We always meet together, discuss, and always presenting, Michał, this is not the end. Again, we need to change something. And again, we need to modify something. And he brings 10 of propositions, how we can change it. So it's always like this. What is the most critical part? How we should prepare our wish list, in order to speed up the process of development, of designing the final form of the product.
That is a difficult question. Thank you. So I think there are two aspects of it. One is the good understanding what you just said, what you can account for when you work with a designer or a designer's team. The thing is that because I have been working with engineers for such a long time, I have maybe a little better understanding of the constraints that a new product development process would take. But then I think the way that to answer your question, about this speeding up the process would be to work very closely at the beginning, because the beginning is the more things you consider at the beginning, and the better you have, the wider the spectrum of requirements is described, the better you can better define the roles, you can better define the dialogue that is happening between engineers and designers. And I think because even with the project you mentioned that you already have had some idea of it, and then I would imagine that if we started together, I think that was the same with the band, that we joined very late and we have a limited time and possibilities. Even though students came up with many different ideas, they were not so visible. But I think that the earlier you start the dialogue and the earlier you define all the pieces and all the risks and all the constraints, the faster and more efficiently the process will happen. So
to follow up on Professor Ulf's question
yes.
and exchange of the respective roles of artists, designers, and engineers. And I think that what he mentioned in responding to your question, the key issue is to begin from this kind of cooperation from the very beginning. With. And what this whole exchange reminded me of a short documentary that I must have seen in the 90s. It was related to the design of the famous opera house in Sydney, one of the architectural marvels. But the challenge in this case was that because the lead was taken by architects, by designers, with no input from engineers from the very beginning. At a certain stage, the designers, the architects, the whole team realized that serious mistakes were made if one of their goals was to have not only the most architecturally beautiful building you can think of, it's an icon in architecture, modern architecture. And the problem there was that to design the best music projection quality, the mistakes were made. It was extremely difficult to correct them. Ultimately, because the engineers became involved too late. So I believe the key, nothing to do with space, but the key issues we are talking about aesthetics, functionality, and engineering solutions. And I believe that functionality has to be the lowest common denominator. And to address it, you have to be literally. And if so, then Professor Ulf's concerns would go away.
Thank you for that comment, and I couldn't agree more. And this example illustrates that it can go both ways. So what you said was designers, architects thinking, having a vision without the understanding of technical constraints, and it happens so many times, and it happens in startups when designers are starting like developing first ideas, and then it turns out that the budget will have to grow 10 times to make it real, and it's unsustainable. And so yes, like to your remark, this is the most important thing, to start at the very beginning together and not waiting one for another, whether it's designer who comes up with the idea or engineer. I think, but also it also really requires a lot of humility and understanding, because we all have egos, and we all kind of think we're gonna propose the idea and the vision, whether there are designers or engineers. So I think that is my experience, that this is very important on both sides, to have humility and to work together from the very beginning. However pathetic it can sound, but it's like, not pathetic, sorry for that word, naive, sorry, that's what I meant. However naive it may sound, this is the idea, I think.
But it's pathetic if it doesn't happen.
Yes, thank you for saving me.
No, we don't.
Okay, so thank you very much once again for a very interesting presentation.
Thank you.